Alright, velkommen tilbage. Vi skal i gang med kapitel 8, som er Common Collections. Så lad os hoppe ind i det. Common Collections. Rust standard library includes a number of very useful data structures called collections. Most other data types represent one specific value, but collections can contain multiple values. Unlike the built-in arrays and tuple types, the data these collections point to is stored on the heap, which means that the amount of data does not need to be known at compile time and can grow or shrink as the program runs. Each kind of collection has different capabilities and cost, and choosing an appropriate one for your current situation is a skill you'll develop over time. In this chapter, we'll discuss 3 collections that are used very often in Rust programs. A vector allows you to store a variable number of values next to each other. A string is a collection of characters. A hash map, which allows you to associate a value with a particular key. It's a particular implementation of the more general data structure called the map. Nice. Hash map. Det er lidt en meme i udviklerverdenen. Fordi at når du er inde til et interview, et sådan algoritmisk interview, hvor de spørger om du kan løse et eller andet problem, så er det typisk, at de vil have, at du gør det med et hashmap. Hvorfor? Det er fordi et hashmap er den mest hurtige, tidsmæssigt i hvert fald, og derfor mest optimalt. Så hvis du kan løse et algoritmeproblem med en hashmap, så gør det. Så består du dit udviklingsinterview. Alright, cool. We'll discuss how to create and update vectors, strings, and hash maps, as well as what makes each special. Cool. Storing vectors. Skal det på den her måde. Common collections. Cargo og cargo new. Common collections. I might is. Okay. Cool. Alright. Alright. Storing the list of values with vectors. The first collection type we'll look at is vect, also known as vectors. Så vectors er det, man kalder for arrays i andre sprog. Og det er noget med, at grunden til, at det hedder vectors i Rust, er fordi de har taget terminologien fra C++, som også kalder deres arrays for vectors. Vectors allow you to store more than one value in a single data structure that puts all the values next to each other in memory. Vectors can only store values of the same type. Alright. They are useful when you have a list of items such as the lines of text in a file or the prices of items in a shopping cart. Alright, lad os se på det. Create an empty vector. We call the vec_new function as shown is listing 8.1. Okay. Så vi laver en vector based on assigned integer 32. New. Så er der lige Rust LSP internal auto-completion. Hvad kan vi gøre med den her? Okay, så vi kan appende whatever vi vil her. Og hvad det her wrong? Wow. What? Rust doesn't know what kind of elements we intend to store. This is an important point. So implementing using generics. Now know that vec_t type provided by the standard library can hold any type. When we create a vector to hold a specific type, we specify the type within angle brackets. Okay. More often you'll create vec_t with initial values. Rust will infer the type of value you want to store. Rust conveniently provides the vec macro. We'll create a new vector that holds the value you give it. Yep. Come on. Okay, so I need to push. Moves all elements of other into self. Okay, så det er push. Det er ligesom JavaScript. What is going on? No errors, beautiful. Alright. Så vi kan skubbe elementer ved at sige push. I stedet for append. Kan jeg vide, hvad append gør egentlig? Moves all elements of other. Self, leaving other empty. Okay, interessant. Reading elements of vectors. There are two ways to reference a value stored in a vector: via indexing or using the get. Following examples, we have annotated the types of the values that are returned from these functions for extra clarity. 8.4 shows both methods of accessing a value in a vector with indexing and the get. Okay, kan vi vide, hvad der sker, hvis jeg accesser noget, der ikke er der? Alright. Så den compiler, men det eksisterer jo ikke. Third element is third. There's no third element. Jeg kan egentlig bedre lide. Det her er mere simpelt, men den kan også godt error. Og vi handler så ikke erroren. Så jeg den her er bedre. Hvor du på get får så en option tilbage. Så matcher den her option. Okay, så er det her. We use the value to get the third element because it starter med index 0. Using borrow and square brackets gives us a reference to the value at the index. Gives us a reference to the element at the index value. When we use the get method with the index value passed as argument, we get option T that we use with match. The reason Rust provides these two ways to reference an element is so you can choose how program behaves when you try to use an index outside of the range of existing elements. As an example, let's see what happens when we have a vector. When we have a vector of 5 elements and we try to access an element at index 100. When we run the code, let's see. Ja, det er så det vi lige har gjort. When we run the code, the first square brackets method will cause the program to panic because it references a non-existing element. This method is best used when you want a program to crash if there's an attempt to access an element past the int. When the get method is passed an index that is outside the vector, it returns none. You can use this method if accessing an element beyond the range of the vector may happen occasionally under normal circumstances. Your code will then have logic to handle either some or none. When the program has a valid reference, the borrow checker enforces ownership and borrowing value, and borrowing rules. To ensure this reference and any other references to the contents of the vector remain valid. We call the rule that states that you can't have mutable and immutable references in the same scope. That rules apply in listing 8.6. While we hold an immutable reference to the first element in a vector and try to add an element to the end, this program won't work if we also try to refer to that element later in the function. Interessant. Okay. Interessant. Interessant. Okay. Vi kan ikke ændre på den. Det ikke giver mening, right? Ikke ændre på den, fordi at den kan ændres senere. Alright, cool. Eller så når vi bruger den her, når vi skubber til vektoren, sker den en error, fordi at vi ikke må skubbe, fordi at den her reference ændrer så sin værdi. Og når vi så bruger den, den her reference senere hen, så er det muligt, at det ikke er det, vi forventer, og derfor får vi en error af compileren. Giver mening. Okay, hvad står der her? Why should a reference to the first element care about the changes at the end of the vector? This error is due to the way vectors work, because vectors put the value next to each other in memory. Adding a new element onto the end of the vector might require allocating new memory and copying the old elements in the new space. If there isn't enough room to put all the elements next to each other, where the vector is currently stored. In that case, a reference to the first element would be pointed to deallocated memory. The borrowing rule rules prevent programs from ending up in that situation. Okay. Iterating over the values in a vector. Skal man borrow? Nej. Gør man ikke. We can also iterate over mutable references to each element in a mutable vector in order to make changes to all elements. Okay. Hvordan printer den ud? Er der en map til den her? Okay, into iter. Interessant. V dot into iter. Dot map. Nice. Laver jeg en funktion her. Du kan sige element. Element plus 1 collect gør det her. Fish type position table fish. Select all right. Cool. Skal der så det er VV er lige med det her. Det er VV, det er en vektor. Er en error eller noget sted? Forstår jeg ikke. Ja. All right. Super nice med map. Så kan man lave nogle functional ting. Change the value. You have to use the dereference operator. Get to the value. Okay. Iterating over a vector whether immutable or mutable is safe because of the borrow checkers rule. If we attempted to insert or remove items in the for loop, we would get a compiler error similar to the one we got from the code. In A6, the reference to the vector that the for loop holds prevents simultaneous modification of the whole vector. Okay. There are definitely use cases for needing to store a list of items of different types. Fortunately, the variants of an enum are defined under the same enum type. So when we need one type to represent elements of different types, we can define and use an enum. Okay. Okay, så vi laver den her enum, der hedder spreadsheet cell, som kan indeholde en integer, float eller tekst. Og vi kan så lave en vektor, der indeholder den her enum. Guess row 2 spreadsheet cell. Hvordan fanden? Big. This is new. Okay, Rust needs to know what types will be in the vector at compile time, so it knows exactly how much memory the heap will be needed to store each element. We must also be explicit about what types are allowed in the vector. If Rust allowed a vector to hold any type, there would be a chance that one or more of the types would cause errors with the operations performed on the elements of the vector. Using an enum plus a match expression means that Rust will ensure at compile time that every possible case is handled. Beautiful. If you don't know what the exhaustive set of a program would get at a runtime to store. If you don't know the... Okay. Så hvis I ikke kender alle typerne på forhånd, så kan vi ikke bruge en enum. Instead, you can use a trade object. Okay. Note that we discussed some of the most common ways to use a vector. Be sure to review the API. Okay. Dropping a vector drops its element. Like any other struct, a vector is freed when it goes out of scope as annotated. Okay, cool. Strings. burde være en måde bare at kollapse alt i VS Code. Would be nice. Okay. New rustaceans commonly get stuck in strings for a combination of 3 reasons. Rust's propensity for exposing possible errors, strings being a more complicated data structure than many programmers give them credit for, and UTF-8. These factors combined in a way that can seem difficult when you're coming from other programming languages. We discuss strings in the context of collections, because strings are implemented as a collection of bytes, thus some methods to provide useful functionality when those bytes are interpreted as text. In this section, we'll talk about the operations on string that every collection type has, such as creating, updating, and reading. We'll also discuss the ways in which strings is different from the other collections, namely how indexing on string is complicated by the differences between how people and computers interpret string data. Alright, what's a string? We'll first define what we mean by the term string. Rust has only one string type in the core language, which is a string slice str that is usually seen in its borrowed form and str. In chapter 4, we talked about string slices, which are references to some UTF-8 encoded string data stored somewhere else. String literals, for example, are stored in the program's binary and are therefore string slices. The string type, which is provided by Rust's standard library rather than coded into the core language, is a global, mutable, owned UTF-8 encoded string type. When rustaceans refer to strings in Rust, they might be referring to either the string or the string slice, not just one of those. Although this section is largely about string type, both types are used heavily in Rust standard library, and both string and string slices are UTF-8 encoded. Alright, creating a new string. Many of the same operations available with vectr are available with string as well, because string is actually implemented as a wrapper around a vector of bytes, some extra guarantees, restrictions, and capabilities. An example of a function that works the same way with vectr and string is a new function to create an instance. Cool. Okay. Often we'll have some initial data that we want to start this string with. For that, we use toString method, which is available on any type that implements the display trait, as string literals do. That in string literal, then come on. There's two, så det må være en string literal, right? Okay. Hvad betyder det for... Because strings are used for so many things, we can use many different generic APIs of strings, providing us with a lot of options. Some of them can seem redundant, but they all have their place. In this case, string from and toString do the same thing. Which matter is which you choose is a matter of style and readability. I think jeg tror jeg bedst kan lide den her toString. Wow. Okay. Alright. Then the pushString method takes a string slice because we don't necessarily want to take ownership of the parameter. For example, in the code, we want to be able to use S2 after appending its contents to S1. If the pushString method took ownership of S2, we wouldn't be able to print its value on the last line. However, this code works as we expected. Men hvad sker der så, hvis vi siger toString? Ja. Det vil ikke. Hvad gør vi så? Let's borrow. Sådan. Concatenation with the plus operator on the format. Man. Der bør søges være en et eller andet. Det gør det nemmere at skrive den her. Det her ud. Oh wow, det kan jeg ikke. Interessant. Så vi skal ja. Så vi skal allokere noget memory, I guess. Så enten skal den bruge så der skal bruge eller noget memory. Right? Så enten skal den bruge den her variables memory, eller skal den bruge den her, eller skal vi allokere noget nyt memory, I guess. Jeg ved, om der er en nemmere måde at gøre det her på. String. Okay. Okay, den måde også gøre det på. In a library, you'll see add defined using generics and associate types. Here we have substituted in concrete value in concrete types, which is what depends on which is what happens when we call this method a string. Okay. S2 has and, meaning that we are adding a reference of the second string to the first string. This is because of the s parameter in the add function. We can only add and string to a string. We can't add two strings together. But wait, the type of S2 is and string, not and string. Why does it compile? The reason we are able to use is and S2 in the call to add is that the compiler can coerce the and string. Okay. Rust uses deref coercion, which here turns and S2 into det her, men det er. Because add does not take ownership of the s parameter, S2 will be a valid string after this operation. Second, we can see in the signature that add takes ownership of self. Because self does not have an and. This means that S1 will be moved into add and will no longer be valid after that. So although det her looks like it will copy both strings and create a new one, this statement actually takes ownership of one, sends a copy of the content, and then returns ownership of the result. In other words, it looks like it's making a lot of copies, but it isn't. Implementation is more efficient than copying. Cool. We need to concatenate multiple strings. The behavior of the add operator is unwieldy. This point, it's difficult to see what's going on. For more complicated string combination, we can use instead. Okay, nice. I can see. This Okay, format. Okay. Okay. Okay, the code generated by the format macro uses references so that this call doesn't take ownership of any of its parameters. Det er interessant for alle macros, at de ikke tager ownership. In many other programming languages, accessing individual characters in a string by referencing them by index is valid and a common operation. However, if you try to access parts of a string using indexing syntax in Rust, you'll get an error. Very nice. Okay. Eller er det? Det ved jeg ikke. Rust doesn't support indexing, but why not? To answer that, we need to discuss how Rust stores strings in memory. A string is a wrapper. Let's look for probably encoded. What the hell? Okay, in this case, okay, så vi laver en string, der hedder holder. In this case, længden vil være 4. Så den er 4 bytes long. Each of these letters takes 1 byte. The following line, however, may surprise you. Note that this string begins with the capital Cyrillic letter Z. Asked how long. Thing is, you might say 12. Rust answer is 24. And there's a number of bytes it takes to encode det her. Because each Unicode scalar value in that string takes 2 bytes. Innocent. An index into the string's byte will not always correlate to a valid Unicode scalar value. Okay. I know that the answer will not be 3, the first letter. When encoded in UTF-8, the first string of 3 is 208 and the second is 151, so it will seem that answer will be in fact 208. But 208 is not a valid character on its own. Turning 208 is likely not what a user would want if they ask for the first letter of the string. However, that's the only data that Rust has at byte index 0. Users generally don't want the byte value returned even if the string contains only Latin letters. The answer then is to avoid returning an unexpected value and causing bugs that might not be discovered immediately. Rust doesn't compile its code at all and prevents misunderstanding early. Okay, men altså hvad gør man så? Hvis man skal iterere over det. Okay, så man skal bruge characters og chars. Rust provides different ways of interpreting the raw string that computer store so that each program can choose the interpretation it needs, no matter what human language the data is in. A final reason that Rust doesn't allow us to index into a string to get a character is that indexing operations are expected to always take constant time, but it isn't possible to guarantee that performance with a string. It isn't possible to guarantee that performance with a string. It isn't possible to guarantee that performance with a string. because Rust would have to walk through the contents from the beginning to the index to determine how many valid characters there are. Okay, indexing into a string is often a bad idea because it's not clear what the return type of the string indexing operator should be. If you really need to use indices to create string slices, Rust asks you to be more specific. The best way to operate on pieces of strings is to be explicit about whether you want characters or bytes. Så I guess de fleste tilfælde vil vi gerne have characters. Hoppa. Jeg ved ikke engang, hvad det her betyder. Getting graphene clusters from strings as with the Devanagari script is complex. Hvad? Alright. Strings are not so simple. To summarize, strings are complicated. Different programming languages make different choices about how to handle this complexity to the programmer. Rust has chosen to make the correct handling of string data the default behavior for all Rust programs, which means programmers have to put more thought into handling UTF-8 upfront. This trade-off exposes more of the complexity of strings than is apparent in other programming languages, but it prevents you from having to handle errors involving non-ASCII characters later in your development lifecycle. Good news is that the standard library offers a lot of functionality built off the string and string types to help handle these complex situations correctly. Be sure to check out the documentation for useful methods like contain for searching in a string and replace for substituting parts. Alright, hash maps. Cool. Storing keys with associated values in hash maps. The type hash map stores a mapping of keys of the type K, values of type V, using a hashing function, which determines how it places these keys and values into memory. Many programming languages support this kind of data structure, but they often use a different name, such as hash map object. Hash maps are useful when you want to look up data, not by using an index, as you can with vectors, but by using a key. Okay. Alright, creating a hash map. Oh, hash map. Skal jeg ikke sige til den, hvad det er? Unknown. Jeg skal ikke specificere typen. Den er bare unknown, det hed. String. And no. Okay. Så det er bare Annie eller hvad? Interessant, den indførte. Interessant, nå det er sgu da meget fedt. Man behøver jo ikke engang... Man behøver ikke at... sige til dem, hvad det skal indeholde. Den kan indføre det fra usage. Nice. Okay, node. We first need to use the hash map from the collections portion of the standard library. Of our 3 common collections, this is one of the least often used, so it's not included in the features brought onto scoping automatically in the prelude. Hash maps also have less support from the standard library. There is no built-in macro to construct them. Okay. Så man henter den med getter. Copy it. Why? Oh, okay. This score will have the value that's associated with the blue team. No value. Null. We can iterate over key value pair in a hash map in a similar manner using a for loop. Hash maps and ownership for values that implement the score traits. The values are copied into the hash map. For owned values like string, the values will be moved and the hash map will be the owner of those values. Okay. Ja, okay, så det vil sige, at jeg kan ikke bruge... Oh man. Ja, nu giver den en error, fordi den her bliver nu ejet. Det her. Karakter, der giver den en error. Okay, den skal eje den. Fair. Although the number of key and value pairs are global, each unique key can only have one associated value with it at a time. When you want to change the data in a hash map, you have to decide how to handle the case when the key already has an assigned value assigned. You replace the old value, completely disregard the old value. You could keep the old value and ignore the new value, only adding if doesn't already have a value, or you can combine the old value with the new value. Okay, so det er en override. Det er en key or insert entry. It's common to check whether a particular key already exists with a value, then take the following actions. If the key doesn't exist, if the key does exist, it should remain. If it doesn't exist, then insert. Hash maps have a special API for this called entry that takes the key you want to check as parameter. The return value of the entry method is an enum called entry that represents a value that might or might not exist. If it doesn't, we will insert. Så. Så hvis den eksisterer. Okay. I see. Insert with key. Hvad resonerer det her? Uh, Oh, that's kind of interesting. The second call to entry will not change the hash map because the blue team already has the value 10. Very nice. Good enough. Understand. What the hell? What? All right. Close enough. Okay, updating a value based on the old value. One common use case for hash maps is to look up a key's value and then update it based on the old value. Hit white space, app entry. Hvis den eksisterer, ellers indsæt den nul. Okay. Alright, så tager den her string, eller den her string slice, er det jo så. Laver den om til en string, eller en array af strings, vector strings. Ja, det er også en makro. En iterator af string slices. Så vi har vores map, og hvis den her nøgle eksisterer, så gør ingenting. Hvis den ikke eksisterer, så giver en værdi af 0. Redirect for den her count, og det kan vi, fordi at den er en mutable, og så laver vi en til. That's pretty nice. Og så printer vi så mange gange den er talt. Okay. HashMap uses a hashing function called ziphash that can provide assistance to DDoS. It is not the fastest algorithm available, but the trade-off for security that comes with the drop performance is worth it. If you profile your code and find that the default hash function is too slow, you can switch to another function by specifying a different hasher. A hasher is a type that implements the build hasher trait. Okay. Ziphash. Alright. Summary. Vector, strings, and hash maps will provide a large amount of functionality necessary in programs when you need to store, access, and modify data. Here are some exercises you should now be equipped to solve. Given a list of integers, use a vector and return the median. Sort it. And the mode, convert strings to Pig Latin. And the first consonant of each word is moved to the end. Using a hash map and vectors, create a text interface to allow a user to add employee names to a department in a company. Standard library API documentation describe methods that vector strings and hash maps will have that will be helpful for those exercises. Getting into more complex programs in which operations can fail is the perfect time to discuss error handling. We'll do that next. Alright, cool. Det var kapitel 8. Common collections. Så vi er snart halvvejs. Kommer nok til at blive sværere og sværere. Cool. Det glæder mig til. Vi snakkes.